And welcome to the lecture video about independent samples t-tests. So we've flirted at all the different types of tests that we'd be doing. And here we are getting into tests very different than how we have been calculating them so far. Up to this point, we've just been doing the one sample T and Z. Now we're going to go deeper into the T rabbit hole and take a look at independent samples t-tests, or two independent sample t-tests, but just to make it faster, I call it independent samples t-tests. Okay, so back last week before, when we've talked about one sample z-tests or one sample t-tests, remember that we were comparing a population, a provided population, to the population of a sample that we were generalizing for. The population was generalized from the sample. So notice that with one sample T or one sample Z tests, they had one sample. That was it. You were provided with one sample size. You were provided with a sample mean, a sample standard deviation if it was a one sample T test, and again, one sample size. With independent samples t-tests, that is not the case. Now we have two samples. So it's kind of in the name in terms of the two independent samples t-test or the one sample Z, one sample t-test, etc. But ultimately, one way that you'll be able to distinguish these tests from another at this point, now that we're kind of moving into a different realm, is going to be independent samples t-tests have two samples in them, meaning that you'll likely see two sample sizes, two sample means, and two sample standard deviations. Okay, nifty, bitchin', cool. So when we say independent samples t-test, so I've addressed the two samples aspect of the two independent samples t-test, but when we say two independent samples is referring to the concept that these two groups, these two samples that we're comparing, that we're looking at, they should not influence the other. The scores or the test scores on one should have nothing to do with the other. So I know in our activity recently, we discussed the providing an experiment of providing half of the students study guides and the other half no study guides, where, you know, I flipped a coin and you either got a study guide or you didn't. Now, that is an independent samples t-test. And why would that be? Well, one, we have two samples. I have, let's say there's 40 of you guys in the class. If I split it down the middle, 20 of you would get the study guide and 20 of you would not. So we have two samples that we're comparing, the group of 20 with, the group of 20 without. And then the independency of it is going to be, I don't think that the test scores of the people who have the study guide are going to have any sort of impact. They're not going to change the test scores of anything with the people without the study guides. You guys take your tests individually. You guys aren't like, you know, swapping study guides, assuming, oh my God, hey, cat is deciding to do stupid shit. Bunny, no, stop it. I love you, but no. So you have these two groups that you're not really thinking that the exam scores for the people with a study guide are going to have any influence on those without. Now, yes, we expect them to be different. We expect the study guide group to perform perform better on the exam. However, that doesn't have anything to do with how they're not dependent on each other. The scores of one do not depend on the scores of the other. We're comparing these two separate independent groups to see how they match up or don't. We're comparing the differences. So now we're going into the realm of, we're no longer provided any information about the population, like we did with the one sample T and Z tests. Remember that we said, oh, on average, Americans or lazy people, or, you know, we just had this generic population that we were looking at, that we were provided the mean for, at the very least, standard deviation if it was a one sample Z test. But now we're not really looking at populations. We don't have the population mean or standard deviation or any of that stuff. Now we're using two samples, two independent samples, and we're using these two samples to generalize to the population in which they are, samples of, and making conclusions regarding those populations. So we compare groups to each other a lot, or at least it's fairly, it's pretty common to do so. So we can compare our class to Professor Greenwood's class. So we can take the exam scores of exam 1 of our class and compare it to a different statistics class. Hell, we can do it from the two classes that I'm teaching, my Monday, Wednesday class, and I can compare that to my Tuesday, Thursday class. We can compare groups of dog lovers and cat lovers, maybe on neuroticism or, I don't know, something, cleanliness, weirdness, whatever, loyalty, independence. We can use an independent samples t-test to test the independence of cat lovers and dog lovers. We can compare different diets. We can compare how people on a vegan diet to people on a keto diet and see which one is more, I don't know, effective for the body, or which one, who talks about it more. We can compare these different groups, but they're independent of each other. Our class test scores will have nothing to do with Christopher Greenwood's test scores. They're not going to have any sort of impact on the other, just like how a cat lover's neuroticism is going to have no impact on how dog lovers' personalities are, or people on a vegan diet. The amount of times they talk about their diet will have nothing to do with how many times people on a keto diet talk about it. Unless they're put in the same room together, then they're just going to be constantly talking about recipes. But the point being that these independent groups are not influencing the other, and we can compare these groups to each other all the time. So I say brainstorming on this. So try and think of some other examples of groups that you can compare to each other and see, kind of see if that works. You can compare anything really. So a key for independent samples t-tests, what makes them independent samples, is the fact that they are using a between subjects design. Now, what this means is that of the two samples that we have for independent samples t-tests, those two samples, the participants within those samples, are different people. So for example, if I were to split the class in half down the middle, 20 and 20, half you get the study guide, half of you don't. Well, the 20 in the study guide group are going to be a completely different set of people than the 20 in the not study guide group. The people in our class are going to be different from the people in Greenwood's class. You're not taking stats, the same Psych 42 class in the same semester. You're not taking more than one class of the same class in the semester. Ooh, that was a really wicked, awful sentence. And now correct me if I'm wrong, but I do believe that people on a vegan diet are not also going to be on a keto diet. I'm not really a diet person. I don't know what goes in. I'm more familiar with a vegan diet than I am a keto diet. But ultimately, people in these separate groups are not going to be overlapping. There's not going to be someone in our class as well as someone who's in Professor Greenwood's class. There's not going to be someone who does not eat any animal byproducts, but also eats meat or, eats keto stuff. I don't know. I don't know. But the people in these groups are completely different from each other. And that's also what makes them independent. We're not comparing test scores with our own class, comparing test scores twice. That's going to be something we talk about with dependent samples t-tests, but rather the people in our samples are different. And that is a between subjects design, which is key for independent samples t-tests. Look for that between subjects design where our groups are of separate, completely different people. And that's going to be, that seems to be like an independent samples t-test. So there are different ways of selecting samples for comparing two groups. And just like how we have the experimental and quasi-experimental research method in psychology that we talked about a while ago, We also have the quasi-experimental and experimental way of selecting samples. And it's actually kind of similar to how we think about quasi-experiments and true experiments. Now, just to be clear, either method of sampling can work to calculate an independent samples t-test. You don't have to use an independent samples t-test with experiments only. It can also be used with quasi-experiments. The statistics, the tests that we use are not specific to the research method itself, like t-test can only be, or independent samples t-test can only be used with experimental methods of psychology. It can also be quasi-experimental. Really what we're looking at is, do we have samples that are independent of each other? Do we have a between subjects design where the two samples, the two groups are completely different people or sets of observations or what have you? If that's the case, we go with independent samples t-test. Hooah. All right. So we'll start with the quasi-experimental way. Now, this is where we're selecting the people that are going to be in our sample from two different populations and compare. So just like how we talked about how quasi-experimental does not have random assignment, when we talked about it in previous weeks, I should say, just how quasi-experimental does not have random assignment to groups. Like if we were going to be looking at age or gender, we don't flip a coin and say, you're going to be 50 today, or we're going to assign you as a trans male today. No, you walk in with the gender or the age or the ethnicity or the whatever you got, you walk in with that and you are placed into the group that goes with who you are, or what you are, whatever. So when it comes to selecting samples the quasi-experimental way, it's going to be from those separate groups of people that are just who they are. So this has kind of a dated reference to gender, and I apologize. But we have comparing men and women on depression scores. We're pulling our samples, our sample of men, our sample of women, from the population of men and women. And we're using that population to generalize, or excuse me, we're using the samples that we obtain from these populations of men and women to generalize about men and women and how they differ on depression scores. Now, same thing can be said with comparing high school students and college students' level of stress. That's kind of similar to age groups. We can't predetermine someone to just be in high school or to be in college. That has a lot of different factors to it, and age can certainly be one of them. But we have high school students as one population and college students as another, and we are obtaining samples of 100 or 12 or whatever our sample size is. We're obtaining our samples from these two separate populations. Now, the experimental way is where we pull our participants from one population and we make a sample from one population. And from that sample that we obtain from one population, we as the researchers are going to split the groups, split that sample we've obtained into groups. So just like how, if I were to do your class and my other stats class, be it if you're Monday, Wednesday, or Tuesday, Thursday, if I were to take your class and give you a study guide, and the other class I wouldn't give a study guide, that would not be an experimental way because I have two separate populations, my Tuesday, Thursday, and my Monday, Wednesday class. That would be a quasi-experimental way. However, if I were to do, put all 80 of my students together, in both of my sections, and then I start randomly assigning you to have a study guide or not, that would be the experimental way. Now, instead of having two separate populations, one of those populations being my Tuesday, Thursday, the other being my Monday, Wednesday, now I just have one population of all my stats classes, so just the two of them. And then from the 80 of you, I split the group. I assign you guys to have or not have a study guide. So there you go. And just as kind of a visual of that information, of that concept, here we have the quasi-experimental way, two separate populations, two samples. And then the experimental way, where we just have the one population that we extract a sample from, and that sample provides us two different groups. So just like how we were discussing in earlier examples, the population of men, population of women, we take a sample of men, we take a sample of women. They're two, I mean, they're certainly independent samples, but they are quasi-experimental. Now, this does not make it any less good of an independent samples t-test, but we do know some of the pitfalls of quasi-experimental, how any causation that we determine isn't quite as strong as experimental. I'm not saying experiments are perfect, because there's always like a nugget of doubt, but ultimately the causal relationship that we can determine from experiments is stronger than that of quasi-experimental. But anyway, now let's say, okay, now we have a population of college students, just college students, or you can, you know, kind of referring to my example earlier, instead of college students, you can put Professor Cooper's stats class or stats students, and then we split a sample, and then some get the study guide and some don't. Or, you know, college students, some are tested in a loud condition, some are tested in a quiet condition, etc. Okay, so I want you guys to come up with some examples of quasi-experimental methods of sampling and experimental methods of sampling. If it helps you to draw them out with the little bubbles, I highly encourage you to do that. You don't have to, but if you're kind of having trouble deciding, is this, you know, quasi or true experimental, the bubbles might help. Or, you know, bubbles just a fun word to say. So now we have to compute this. Now we have to determine differences. So, you know, with some of our examples, it's been, oh, you know, who performs better on the exam? Students who have the study guide, students who don't. And those are our two samples, students with and without the study guide. And we're comparing them on test scores. We talked about depression scores between men and women. Now, we could, to make it an independent samples t-test, we would just have two samples. So we can really pick any two genders we want and put them in there to compare depression. But ultimately, we know kind of how to set, we know what it is to have an independent samples t-test. We're comparing two different groups, two independent samples to another to see how they compare. Now, when we compute it, we have to have assumptions. We have assumptions that we have to assume before we get into it. So the first is normality. So the data in the populations or population, you know, if it's quasi, we have two populations, men and women, Tuesday, Thursday, Monday, Wednesday class. If it's true experimental, we have one population. So my stats students, maybe Fresno State students, or however you want to break it down. We assume that the data for the populations that we're sampling from is normally distributed. Now, do we know this for certain? No, but we assume it. We also assume, and this is the funny one, we assume that the data we obtained for our samples has been obtained through random sampling procedures. Now, that's not true. That's not true. There's a difference between random sampling and random, I was going to say selection, random assignment to groups. Random assignment to groups is where, oh, you know, just like, oh, I have all 80 of my students, and for each of my students, I flip a coin, everyone has the same probability of getting or not getting a study guide. That's random assignment. But random sampling is different. So random sampling is essentially saying, instead of every person in your study having the same probability of being in one group or the other, random sampling is saying every person in the population you're testing has the same probability of being selected for your study or for your, you know, your research, which in the case of the population being in the example that I've been mentioning of the population being just my stat students, random sampling is easy. I only have like 80 and I have easy access to those 80 students. However, remember that this is psychology and we often have large populations because we're trying to state, you know, we're trying to have these overarching, you know, theories take place. We're trying to describe behavior for big groups of people, not just, you know, 80 people in Fresno, California. Where's Fresno? California? I thought that was all beaches. No, Fresno is a shithole. But ultimately, random sampling, remember, in psychology, we have big populations. So if our population was college students just as a whole, random sampling would be saying every single college student in, let's say, the United States, let's make our population college students in the United States. Every single college student in the United States has the same probability of being selected for your study as any other. And that's just not true. I mean, people that go to Fresno State are certainly going to have a higher probability. People you know, maybe you send out your survey to them or recruit them through some sort of method. Those people are certainly going to have a higher probability of being in your study than some random dude at community college in Montana. Like, I don't know that guy. So there you go. We assume random sampling, but I just think it's funny because I just think it's funny. Just like how, when we were talking about the theoretical sampling methods in terms of finding all the possible samples, when we talked about characteristics of the sample mean, I mentioned how, when we use inferential statistics, we tend to go with the theoretical side. We tend to go in that statistical la la land where it's like, yes, in a perfect world. Of course, it's not. Random sampling, the assumption of using random sampling in independent samples t-test kind of follows that same suit. In a perfect world, we would have random sampling because then you'd have a truly unbiased population, or sample that you've selected from. But that's not the case. That's not the case. Next, obviously, for independent samples t-test, we're going to assume they're independent. That's the name of the game, dude. So one group is not going to influence the other. And then equal variances. This is similar to, well, actually, no, it's not. So the variances within these two populations or within the population that we're comparing, whatever, we assume that the variability, again, variance is a measure of variability, within these populations or groups of people that were, or the samples that we are generalizing to populations, we assume they're equal. Hello, I'm trying to scroll. Thank you. Okay, now let's take a look. Let's take a gander at this. So here is an example of an independent samples t-test problem. So one strategy to reduce food intake is to eat slower. To test this strategy, we compare two groups eating at the same buffet, two groups within our population of people eating at the buffet. One group is instructed to eat fast, the other is instructed to not. They're instructed to eat slowly. We record the number of calories consumed by the group instructed to eat fast. They have a mean of 650 calories, a standard deviation of 130.38, and we have a sample size of 6. So there are 6 people in this group. And the slow group has a mean of 600 calories consumed, a standard deviation of 154.92, and this group also has a sample size of 6. Now we want to test whether the rate of eating, either slow or fast, influence the amount of calories consumed, where our alpha, of course, is 0.05. So we measured the amount of calories that each group ate, and we found the mean for it, 650 calories consumed for the fast group on average, and then 600 for the slow group. So now we are using an independent samples t-test to test to see whether how fast or slow you ate influenced the amount of calories we consume. So we're trying to see who ate more on average. And yeah, we're going to use that statistically. Now, obviously, we can see the mean is 650 for the fast group. So, it's bigger, so obviously. But we got to calculate an independent samples t-test to know if this was just by chance or if this was a very low probability that if these groups were the same, again, the null hypothesis, if these two groups ate at the same rate, there'd be an incredibly low probability that we would obtain a sample mean this high or this low for the slow eating group. If these two rates of eating had no influence on the amount of calories consumed. So again, we're going to do a hypothesis test, just like we've been doing with one sample T and Z. Now, just to visualize it, now the problem did state that we're looking in the same buffet and we take the people eating and just split them down the middle. Some are instructed to eat slowly, some are instructed to eat fast. So we have an experimental method of gathering our sample, creating our samples. Because again, our population is just people that were in the buffet patrons. So we take those people and then we split it to half of them are going to eat slow and the other half are going to eat fast. Now you'll see I have some notations here. This is another point in independent samples t-tests. Since we have more than one sample, hence 2 independent samples t-tests, we are going to have notations of 1 and 2 to distinguish our first sample and our second sample. Now I have a lot of students ask, does it matter which group is which? Like, does it matter which sample you list as number 1 and which sample you list as number 2? No, it does not. That's pretty arbitrary in terms of it. I could have easily had the fast eaters be group 1 and the slow eaters be group 2. Just make sure that when you do, make that decision of group 1 and group 2, that you make sure you keep their information together. So, we see here that the mean of the slow eaters is 600 and their standard deviation is 154.92. You wouldn't want to mix up the information and say, oh, the mean for the fast eaters is 600 and the standard deviation is 130.38. You want to, if you have the fast eaters as group 2, make sure all of group 2's information is listed as the 2. It's just kind of keeping your ducks in a line. All right, so of course we state the hypotheses. That's what we always do with these inferential tests that we're working on. Now, with independent samples t-tests, it's a little different. We don't have a provided population mean like we did with the 1 sample tests of weeks past. Now we have 2 independent samples of each other. We have 2 samples. However, we have no information on the population because, again, we are using these samples to generalize to the wider population. Now, I know that it's interesting because you would think, well, with the quasi-experimental way, we had 2 populations. So I understand generalizing 2 samples when we have 2 separate populations, like men, women, or, any gender to any gender. So what's going on with quasi? What's our populations? I thought we only had 1 population of people and they were the buffet patrons. I am so confused now. Well, actually, Megan, actually, we have 2 populations that we're looking at. We're looking at the rate. Remember, our groups were the rate of eating, where one was eating slowly and the other was eating quickly. So now we're trying to compare, we're using a independent samples t-test to see the effect of how fast or slow you eat and how much calories you consume. So we have 2 populations actually now. We have people who eat slow and people who eat fast. And when we finish calculating this independent samples t-test, we'll be able to conclude that the rate of eating either has no effect on the number of calories consumed per meal. So that would be the null hypothesis I'll get to that. Or it is going to be the alternative hypothesis where the rate of eating does have an effect on the number of calories consumed per meal. Our populations are not equal. Now, when it comes to null and alternative hypotheses for independent samples t-test, here's the easy part about it. Every single independent samples t-test has this exact null and alternative hypothesis. mu1 equals mu2 for the null hypothesis, and then mu1 does not equal mu2 for the alternative. Makes it super easy. You don't have to put the right mean down from the population like we had to do for the 1 sample test before. Now it's just mu1 equals mu2 for the null, and mu1 does not equal mu2 for the alternative. Boom, done. Okay, so we need to set the criterion. All of this, so far so good. All right, okay, let's do it. I got a boo. But we got to set the criterion. So we got to know what the degrees of freedom is. It is an independent samples t test. So we do have to use the t table to find our critical t values. And to do that, we have to find the degrees of freedom. Now, there are three different ways. Oh, my eye itches. There are three different ways to calculate the total degrees of freedom for independent samples t-tests, but all of them are going to give you the same number. As long as you calculate it correctly, it's going to give you the same thing every time. Now, the first way is to find the degrees of freedom for your first group and add it to the degrees of freedom for your second group. Second way is just basically the same exact thing, but with more steps, or really just explaining what the step is. Number two is essentially saying the exact same thing as number one. It's just putting the formula in for degrees of freedom. So number two is saying you take your sample, your first sample size and subtract one, plus your second sample size and you subtract one. Or the way I like to do it, I don't know why I do it this way. It's just easier for me. Or, I mean, you know, whatever floats your boat, is just taking the total number of people in your group, in both groups. That would be your capital N. Lowercase n is individual samples. So the fast group and the slow group, or the, you know, Monday, Wednesday class versus the Tuesday, Thursday class. Those separate samples are characterized by N1 and N2. And again, whichever one you classify as the first or second sample is up to you. Just make sure you keep all the information together. But the third method of finding the degrees of freedom is just taking the total number of people in both groups and subtracting 2. Simple as that. So we had 6 people in our slow eaters and 6 people in our fast eaters. Here's all the different ways that you can calculate the degrees of freedom. So again, the degrees of freedom for the slow eaters is going to be 5, plus the degrees of degrees of freedom for the fast eaters is going to be 5 as well. 10, 10, 10. Yeah, anyone that works for you, just as long as you end up getting the same answer. Or well, not as 10, we're going to have different problems, obviously, but as long as you get the correct degrees of freedom, it doesn't matter which of these 3 formulas that you use. Anyway, so we've concluded that our degrees of freedom for this problem is indeed 10. Since we have 2 samples of 6 each, we can subtract 2 from 12 and get our degrees of freedom of 10. Now that we have all the information we need, our degrees of freedom, we know it's a two-tailed test because we looked at that alternative hypothesis saying not equal to. And then we have alpha, our level of significance, set at 0.05. I've already looked in the t-table, and our critical values are plus minus 2.228. Now you can look at the t-table right now, look in the degrees of freedom row for 10, and look in the column that has the two-tailed test with alpha set at 0.05. You're going to find it at plus minus 2.228. Now that we have that, now it is time to calculate or compute the test statistic. Now, this is not the same as one sample T or one sample Z. However, if you just take it slowly, one step at a time, we'll get it. You know, it's a long, kind of irritating process, but it will be done. So we have to do 3 things when it comes to calculating the T statistic for independent samples t-tests. First, we have to calculate the pooled sample variance. Then we must get the estimated standard error of the difference, different from just the estimated error. Then we have to do the test. Finally, we can plug all this information into the T to find the T statistic. Now we have to do it in this order because we need the pooled sample variance to calculate the estimated standard error of the difference, and we need the estimated standard error of the difference to calculate the T statistic. So you need to do it in this order. Now, how do we do that? First, let's start with the pooled sample variance. Keep in mind, there's also the cheat sheet, the inferential statistics cheat sheet, if you want to see like the words written out in terms of what these notations mean. But that S squared P is referring to the pooled sample variance. We know it's the sample variance because it's the lowercase and italicized S squared. Remember, S alone would be standard deviation, but standard deviation squared is the variance. So that S squared here refers to the variance portion, and the P is referring to the fact that it is pooled. Now, what the hell does that mean, pooled? Let's get into it. Basically, we're putting the variances together. So we have the pooled sample variance, S squared P. Okay. Now, here, there are two formulas for the pooled sample variance. Oh my. So there are two different formulas for the pooled sample variance. Now, how do you know which one to use? Well, look at the sample sizes. If the sample sizes are equal, meaning that they are the same size, you would use this second formula. It looks so much nicer, doesn't it? It looks a lot easier. If your sample sizes are not equal, then you would use this one. So keep in mind that it's not just an automatic, oh, I have to use this formula for pooled sample variance. You have two different formulas to choose from, and it depends on if your sample sizes are equal or not. Now with this problem, we have a sample size of 6 for the slow group and a sample size of 6 for the fast group. So we know that we are going to use this information here, the pooled sample variance formula for equal sample sizes, since indeed our sample sizes are equal. Now, if one of them was 7 and the other one was 6, or, if they were just not equal, doesn't matter what the numbers are, if these two sample sizes were not the same, we would have to use this top formula up here, but we do not. So let's stick with this one. So here we go. We're using the pooled sample variance formula for the equal sample sizes. Now I have it written out here. So we are going to take the variance of group 1 and add it to the variance of group 2 and divide that by 2. Because keep in mind that that S squared here, S squared, that's referring to variance. Now the 1 and the 2's on the bottom, again, refers to the group number that we're referring to. But this S squared, variance. Now, also remember, we do not have variance. We do not have variance here. We have the standard deviation. So when you're calculating pooled sample variance, you want to make sure that you are indeed calculating the pooled sample variance. So the reason why we have this 154.92 squared plus 130.38 squared is because we are taking the variance of our groups. Standard deviation squared equals variance. So we have our 154.92 squared plus 130.38 squared divided by 2. I've done the math here, but I've written it out just so you guys can kind of follow along. But that 154.92 squared, 24,000.21, 130.38 squared, 1,698.94. Divide that by 2, and when you add it, and then you divide by 2. That gives us a pooled sample variance of 20,499.58. I'm just going to write that down. 20,499.58. That's our pooled sample variance. Okay. Cool. Now what? Well, notice this is step 1 of 3 of calculating the test statistic. So now we go on to step 2, which is going to be finding the estimated standard error of the difference. Now, again, keep in mind this notation. This SM1 minus M2 is referring to step 2 of calculating the test statistic, which is finding the estimated standard error of the difference. So we have SM1 minus M2. Again, if you forget what the hell these things mean, or I know all the notations get kind of confusing when it comes to statistics, refer back to the inferential test cheat sheet. That'll give you not only all this information, but also write it out in like plain English in terms of what these notations represent, in case you forget, in case you don't want to go back to the notes every time. Just look at that cheat sheet and that should help. So luckily for the estimated standard error of the difference, we only have one formula to use, unlike the pooled sample variance where we had to, frickin' see if we had equal or unequal sample sizes. Not that that's a difficult task, but you do have to use the different formula if they were unequal. But for estimated standard error of the difference, the formula is the same. And I did mention before getting into this that we had to do it in this, we had to calculate these different things in this particular order, because we had to calculate pooled sample variance first, because that calculation is used when we calculate the estimated standard error of the difference. Well, I wasn't bullshitting you. Here it is. So the formula for the estimated standard error of the difference is the square root of the pooled sample variance divided by the first sample size plus the pooled sample variance divided by the second sample size. So I have it written over here in case, just to kind of keep us all on track. So the pooled sample variance, again, what we just calculated in the first step of finding the t-score, we got that to be 20,499.58. So I've just plugged that number in on both parts for the pooled sample variance, because it's the same thing twice, and divided by 6 for the first sample size and 6 by the second sample size. Now, again, it's just the exact same thing because the pooled sample variance, we were using it twice, and we have the same sample size in both groups. So it just kind of looks like we're repeating ourselves, which we kind of are. So we calculate that 3,416.6 plus the same thing, 3,416.6. That gives us 6,833.2. Finding the square root of that is going to give us the estimated standard error of the difference to be 82.66. Oh my God. So after all that, the estimated standard error of the difference is 82.66. Not too bad. Not too bad. All right. Guess what? Now we're on the last step. And this, thank God, is the easiest one, the t-statistic, because damn, we paid our dues with steps 1 and 2 of finding this damn thing. So now the formula for the t-statistic for an independent samples t-test is where we're going to take our mean of group 1, subtract it by the mean of group 2, divide it by the estimated standard error of the difference. Now, that's easy, considering we've already done all of the hard work related to that. So now our mean of group 1 is 600, subtracted by the mean of group 2, the fast group of 650, divided by 82.66. That gives us a t-statistic of negative 0.60. We're done. Well, at least with step 3. All of step 3. All 3 steps of step 3 we've completed. Now, finally, we make a decision and this ends, right? So we are now going to compare our t-statistic, as we do, to our critical value. Now, keep in mind that it's negative. Our t-statistic is negative, so we're going to compare it to the negative critical value. Now, just as a little brief reminder of what that looks like, in case you get a little confused, since now we are going to be dealing with critical values. Bunny, get away from my stuff. Okay. So as per usual, my graph is not to scale, but I have written the critical values. The shaded regions are where you would reject the null hypothesis, where you'd find statistical significance. Now we have the shaded regions again being less than negative 2.228 and greater than positive 2.228. Now, anything that the light does not touch Simba, or I guess I should say that the dark does not touch Simba, is where we retain it. So I kind of wrote in there, it's kind of hard to see. And again, it's not to scale, but I wrote 0 just kind of in the near center, just, to kind of have an idea. And that negative 0.60, again, our t-statistic that we just calculated through our blood, sweat, and tears, that is where it would lie. That is approximately where the t-statistic would lie on this distribution. Now, that's not in the shaded region, is it? That's not where the significance level is. That's not where the significance region is. Again, if it's greater than positive 2.228 or less than negative 2.228, that's going to be a significant difference, or we're going to reject the null. That's not the case, though. It was right smack dab in the middle. So we don't. We would retain the null hypothesis. So that tells us, if we go all the way back to step one, where we looked at the null and alternative hypothesis, by retaining it, we're saying that there is no difference between the rating of there's no difference between eating fast and slow. The rate in which you eat does not have an effect on the number of calories that you consume per meal. That's the conclusion. We retain the null, and that is what the null is telling us, that no matter how fast or slow you eat, that does not have an effect on how many calories you consumed. Now, we have an incredibly small sample size with 6 and 6. So in terms of being able to generalize this to a large population, you generally don't want to have such a rinky-dink tiny sample size. But, you know, for the purpose of this example, then, you know, it works. Just to kind of get us familiar with t-tests. Now, I'm not going to calculate this one. I want you guys to do this on your own and see how you do. I am more than willing to go over it if you might like me to. But for now, I want to get into Cohen's D for independent samples t-tests. So this is if you're following along with the PowerPoint, I have just skipped over to independent samples t-test part 2. You'll notice that the first several slides is actually, you know, kind of going over what we just literally did. So pardon me if I don't have 2 videos, me going over the exact same thing again. But, you know, we've already calculated this. You know, we did our estimated or our pooled sample variance, estimated standard error of the difference, t-statistic. Oh man, we retain the null hypothesis. There's no difference between people who eat fast or slow when it comes to the number of calories they consume. Boom. Now we do Cohen's D, and it's estimated Cohen's D. But if you call it Cohen's D, I'm not going to be persnickety about it. It's a measure of effect size either way. So our estimated Cohen's D is, again, a measure of the effect size for our 2 independent samples t-tests. Now, you got to do Cohen's D last, because the stuff that you need to calculate Cohen's D is, you know, you do in step 3 of the hypothesis testing when you calculate the t-statistic. And I don't want you guys to start, like, you know, get halfway through calculating the t-statistic and then break off to do Cohen's D and then come back, because it's really easy to get confused. So just go through all the things and then do Cohen's D later. So Cohen's D, you were just subtracting one mean from the other and dividing it by the square root of the pooled sample variance. Okay, again, that's what that S squared P is, the pooled sample variance and the square root of that. So if we plug in the numbers from what we did, so again, you know, if you've been taking notes, which I highly encourage you to do, you can see that this pooled sample variance is what we got from the problem that we just did about the fast and slow eaters. So our mean for group 1 was 600. Our mean for group 2 was 650. So that's where we get the 600 minus 650. And we are taking the square root of the pooled sample variance. Again, I've kind of written out the formula again here just to kind of keep us fresh, and then just kind of did it again. But we have 20,499.58 and finding the square root of that. So that equals negative 50 divided by 143.18. And that gives us a Cohen's D of negative 0.35. Whew, nice. It's not too bad. So with Cohen's D equaling negative 0.35, that is a medium strength effect size. Keep in mind that the positive or negative sign does not matter when it comes to determining the strength of Cohen's D. Ignore it. Ignore the positive or the negative sign if it helps. or just know that negative 0.35 has the same exact effect size as positive 0.35, which is still medium. Really, the negative or the positive sign in Cohen's d is just which, did you subtract the big one or did you subtract the little one? Because remember, like I said earlier in this lesson, I said it doesn't matter what number, what group you put as group 1 and what group you put as group 2. I just happen to put the slow eaters as group 1 and the fast eaters as group 2, but I could have just as easily done it the opposite, where the fast group was group 1 and the slow group was 600. Damn it, group 2. And if I would have just flipped it, it would have been 650 minus 600, and that would have given me a positive Cohen's d. But it's still the same thing. It's still a medium effect size. Really, again, like I said, the positive or negative aspect to an effect size for Cohen's d. Cohen's d is the only one where the signage, the positive or negative, doesn't really tell you much, other than, oh, big one came first, or oh, big one came last. That's really what it's telling you. Okay, now that I've ranted. So we have a medium effect size. However, remember that with Cohen's d, the medium, strong, small, whatever you want to call it, that does not have anything to do with the significance of it. Keep in mind that we retain the null hypothesis for this question with our t test, or our t statistic being negative 0.6. So with that, we retain the null hypothesis, which does not make this a significant effect size. If we rejected it, it would be significant, but we didn't, so it's not, so we can't say that. And there you go. So I want you guys to, again, calculate another independent samples t-test here, as well as doing Cohen's d. I know that there was an example earlier in the first PowerPoint. If you would like to calculate Cohen's d for that as well, I mean, go for it. I encourage you to. But that concludes our lecture today on independent samples t-tests. So if you have any questions, don't hesitate to stop by my office hours. Maybe if you want to check your answers on these, on the practices within the lecture, please come to my office hours so we can discuss it. But until then, that is all I have for you. So don't forget to like and subscribe. Oh yeah.